Okay, we are now in the final topic for chapter 3. Okay, it's gonna call linear approximation and differential. The thing that we're gonna do is gonna be we're gonna use the tangent line at x equal to a. Okay, so we have the tangent line at AFA given by is gonna be just the slope equal to so you'll be able to find the slope. It's going to be your f prime a. So this one will give you slope, right? So you have the slope of this tangent line and you use point slope form. So this one will be the equation of the tangent line. And you're going to use this tangent line in order to give approximation for the function. It's kind of, hey, what is what? So this is the picture that I will explain you everything. Okay, so in this case, you're gonna see that you have the point AFA and this guy is give you the tangent line. Okay, so let me write down this one is the tangent line first. Okay, and you have your function fxy equal to fx here. So for this one, you have something like this. Okay, so you have something like this, and you see that if you like, so at this point, it's going to be AFA. I'm not going to do anything yet. But if I want something here, okay, if I want something here, for example, like let give you one function y equal to square root x plus 2 plus 1. Okay, if I have y equal to square root x plus 2 plus 1. Okay, and here I have 2. Okay, here I have 2, and here for this point, let me enlarge this guy a little bit. Okay, so if I have this guy at this point 2.5, okay, so let's say this guy is 2.5. It seems far, but not far. Okay, so you have 2.5 here. So this one, if you like to know f2.5, f2.5, you're gonna see that it's gonna be square root 2.5, okay, plus 2 plus 1. So it's gonna be square root 4.5 plus 1. And this thing is difficult to compute. Okay, so this guy is difficult to compute. It's going to be about 3. I know it's going to be about 3 something. Okay, so it's going to be about 3 point something. So it's kind of difficult to compute. However, you see that the function at 2 is okay to compute, right? So f2 will be square root 2 plus 2 plus 1. So it's going to be 3 basically. Okay, so this guy will be equal to 3. So this one f2 is easy to compute, but f2.5 is difficult to compute. So what we're gonna do is gonna be we gonna use the point on the tangent line at 2.5 instead. So this one is L at 2.5. Okay, L at 2.5, this thing is easier to compute. I'm not gonna say easier because it's just easy to compute. It's easy to compute, okay? Because it is on the line and everything linear turn out to be on the tangent line. Okay, so let on the tangent line and everything linear turn out to be easy to work with, right? So in this case, we gonna estimate f at 2.5 by using L at 2.5. You may say that, hey, or you're gonna get some error. Okay, so this one, you're gonna have some more error. But it's turned out to be good. So it's gonna be some more error, but good. Okay. So for this one, this is what I'm trying to say here, that you're gonna use Lx. Okay, so this one is Lx in order to estimate, okay, in order to estimate the value of the function at x. This one is called linear approximation. Okay, this one is called linear approximation. Okay, so the explanation is on this picture, and I hope that it is clear what am I doing. So we be able to find the slope of the tangent line. Okay, so we be able to find this tangent line at AFA, which is easy to do, and we're gonna use this point on the tangent line as our approximation. So you have to keep that in mind. Okay, let's do one example. Okay, so try to finish this one. If you have y equal to root x plus 2 plus 1 like this, can you find this tangent line for me? Can you find this tangent line for me? Let me use the green color here. So you get y prime equal to 1 over 2 root x plus 2. Okay, and you have y prime at 2 given by 1 over 2 root 2 plus 2. So it's going to be 1/4 for my slope. Okay, so you use point slope form. Okay, so the tangent line is, okay, so this point is at 2, 3, right? So this point is at 2, 3. So it's gonna be y minus 3 equal to 1/4 x minus 2. So you get y equal to 3 plus 1/4 x minus 2. And this one will be your Lx. Okay, and you're gonna compute L 0 2.5. So L 2.5 in this case is gonna be 3 plus 1/4, and you have 2.5 minus 2. You see, where did I put my x? Okay, so this guy is my x here. And then what? And then you're gonna just have L 2.5 is going to be 3 plus 0.5 over 4. Okay, so it's going to be 3 point and 5 over 2. So it's going to be 1.125, right? So it's going to be 125. And you see that this one is easy to compute by hand. Okay, so this one will give you the approximation of square root 4.5 plus 1. Okay, so this guy is kind of difficult to compute. This one is square root 4.5 plus 1. Okay, so it's turned out to be about 3.125. Okay, this one give you approximation. Let's do this example. You like to find the linearization of the function fx equal to square root x plus 3 at a equal to 1. Okay, so let's first do this one. So we like to find linearization of this function at a equal to 1. So you need Lx basically. So you just f prime 1 for the slope. It's going to be 1 over 2 root x plus 3. Sorry, it's going to be f prime x first. So you get f prime 1 equal to 1 over 2 root 1 plus 3. So it's going to be 1/4. So it's going to turn out to be 1/4. And in this case, you're going to have f. So this one will be your slope. Okay. and you're gonna have the point. Okay, so the point in this case is gonna be x equal to 1. Okay, so x equal to 1, f1 equal to root 1 plus 3 equal to root 4 equal to 2. So the point is 1, 2. Okay, so you have the point is 1, 2. So you get the point slope form, the tangent line is y minus 2 equal to 1 quarter x minus 1. So you get y equal to 2 plus 1 quarter x minus 1. And this will allow you to get Lx. Okay, so this one will be the linearization Lx. Okay, so this one is your Lx. So Lx is this guy, and the question asks you to approximate the number square root. Okay, so you need to approximate. So you need to approximate square root of 3.98 and okay, square root of 4.05. So you see that this one is 1 for x equal to 1, right? So square root 3.98 is going to be equal to 0.98 plus 3. Okay, so this guy is f 0.98, right? So it's f 0.98, and f 0.98 is going to be about here, right? It's going to be very close. Actually, let me make this one very close to 1. Okay, and this one is 0.98. I need this guy bigger. That my 0.98. So you see that one, okay, it's very close to 1. And you see that this one, by using our linearization, we're going to be able to approximate this guy by using L 0.98. And L 0.98 is going to be 2 plus 1 quarter 0.98 minus 1. Okay, and this guy will be 0.02. Okay, and this one will be 2 minus 0.02, right? 0.02, so it's going to be 0.005. Okay, 0.0, sorry, it's going to be 0. So this one is 0.02 divided by 5. So it's going to be correct. So it's going to be 0.05. Okay. So this guy will be equal to, okay, so this guy will be equal to 1.995. Okay, so that is going to be the approximation. How about square root 4.05? So this guy will be square root of, so you need 4.05, right? So it's going to be 1.05 plus 3. So it's going to be f 1.05. Okay, and this guy is about L of 1.05. So you're gonna estimate by 2 plus 1 quarter, and you have 1.05 minus 1. So it's going to be 2 plus, and you have 0.05 over 4. So this guy will be, I need 2. Okay, so it's gonna be 2.0125. Okay, so it's gonna be 2.0125. So for this one, you divide 5 by 4, so you get 125. Okay, so it's correct. So this one, you get this approximation. Okay, so you see this one, that this one, let me put where my 1.05 is. So 1.05 is further a little bit. So this guy is 1.05. And you see that it's going to turn out to be very close to the real value. Okay, so you see that it's turned out to be very close to the real value here. So for the thing that we are doing here, I use two color. I will use the green color. So for square root of 3.98, okay, we have x equal to 0.98, and you see the actual value and the value from Lx. So from Lx is going to be 1.995. The actual value turned out to be 1.9949. So you see, you not be able to see the difference on the graph at all. It's almost exactly the same. Okay, so this one will give you a good approximation. Okay, so this one turned out to be good approximation. Very, very good actually. Okay, so the digit turned out to be like if you like to have 3 digits, it's correct up to 3 digit decimal. Okay, and for square root 4, okay, it's not estimate. And another one that I use the pink color. Okay, so I have 4 point square root 4.05. So you have x equal to 1.05, and you see that the actual value is 2.1246. However, you see the estimate that you get from the linearization turned out to be 2.0125. So this one is also good. Okay, so this one is also good. Okay, and you see that square root 4.1. So if you like to compute square root 4.1, you use x equal to 1.1, put into my Lx, is going to be 2.025. And you see that 2.025, you still get actually 3 digit, correct? So this one is also good. Okay, if you want 3 digit. Okay, so you see that if you go further, square root 5, okay, so you have x equal to 2, x equal to 2, x equal to 2 may be far away here, so x equal to 2. So you see when x equal to 2, you're gonna get a bigger gap, okay, so you get the bigger gap. So the gap here turned out to be bigger. Okay, so the gap turned out to be bigger. Gap or error. Let me say bigger error. Okay, so this one gives you a bigger error in this case, and you see this one turned out to be kind of not quite good. Okay, so for this one, I'm gonna say bad. Okay, because it's 2.25, this one you get 2.24. Okay, it's not quite correct. And for the further one, okay, so if you have 6, square root 6, so square root 6, you use x equal to 3, so you see that it's going to be very bad approximation, because on the tangent turn out to be 3, on the tangent turn out to be very far away. Okay, so you see that if you have the, it's going to be bad. Okay, so this one is bad. Okay, this is what we can see from this approximation. Let me do small like this, and this one I'm gonna say bad. Okay. Okay, so in this case, you see that for these two guys, it's gonna be bad for when you have x far away from 1. Okay, so the reason why we have bad error or bigger error because it's further away from my 1. And you can see from this tangent as well, you have some small, you're going to have the bigger error when you far away from this point, because it's at the tangent line is touching, however it's going to be further apart all the time, so it's gonna be bad. So the thing that we gonna have to understand will be we gonna be able to give a good approximation when it's very close to the tangent point. Okay, it's going to be very good approximation. So this will give you the concept of the differential. If you have y equal to fx is a differentiable function, then the differential of differential dx is an independent variable. That is dx, okay, can be given by the value of any real number. Okay, so what is dx? Dx is going to be the difference in x. Okay, dx will be the difference in x like this, and you have dx, and this guy gonna give you like a error. Okay, so this one is going to be the error that you gonna have delta x here that gonna tend to 0. It's going to be very close to x. Okay, and the differential dy is defined in terms of dx as the equation dy equal to f prime x dx. Okay, so dy equal to f prime x dx. So this one is kind of difficult to understand why we need this differential. The thing that we gonna understand will be the dy and f prime x has relationship in the way that you see the slope here. So this one is going to be raised and this one is going to be run. Okay, so the slope turn out to be raised over run, as you may have seen in your high school math before. Okay, so this one is going to be uh, raised over run. Okay, and this guy will be equal to dy over dx. Okay, this guy will be equal to dy over dx. However, the slope can be using derivative to compute as well. The slope can be equal to f prime x when we use the derivative of the function. So in this case, you're gonna have dy equal to f prime x dx. Okay, so this one is the meaning of this guy, and this one you have delta x will tend to 0. Okay, so it means that error will going to be small in this case. Okay, so when delta x going to 0, it's gonna turn out to be dy gonna be about delta y. Okay, so dy and delta y will be the same, and it's gonna make your error here. We need this error to be good. Okay, so error must be small. Okay, so this is what we have here. So we like to first try to find differential. Let's talk about what is differential. The differential is going to be in notation of calculus is going to be dy. Okay, so this guy is differential. And you're going to have dy equal to f prime x dx. So for this one, if the question asks you to find differential, you're going to have dy equal to f prime x dx. So in this case, you differentiate this guy. So it's going to be the first derivative of the second plus the second derivative of the first, and then you have dx. Okay, so this one is dy. So dy will be the notation for the integration as well. Okay, so this is the thing that we're going to use in the near future about integration. Okay, so for dy it's turned out to be square root x minus sine x plus cos x 1 over 2 root x. Okay, so let me explain this one a little bit. The previous figure shows that if we let dx equal to delta x, then the corresponding rate of change in y is going to be delta y equal to fx plus delta x minus fx. And I explained already that the slope equal to raise and run, and you have dy equal to f prime x dx. So this is what it means. Dy represent the amount that the tangent line raise of 4 change in linearization, whereas delta y represent the amount that the curve raise of 4 when x by the amount of dx. So here, normally, when dx or delta x gonna turn out to be small, the concept of the derivative d here, so the concept of derivative d will be using limit h go to 0. Okay, and when you have the something, okay, it's differential, so you have limit h go to 0. And what is h? H will be this distance. Okay, h will be this distance, so it means limit delta x going to be 0. So when you have delta x small, so this guy turned out to be identical, turned out to be the same concept. Okay, so turned out to be the same concept. So this is why I say that delta y is about dy become a better as x smaller. Okay, so this is the reason why do we have that table before. Let me highlight the green. The approximation delta y dy is will be better as delta x smaller. So this guy give you the reason why we have good approximation or bad approximation. Let's finish this one and we're gonna go to the next example. So you have y equal to x squared log x. So you get dy equal to this guy prime. So it's gonna be 2x minus 1 over x dx. Okay, so that's all. We have for the next one, we like to compare the value delta y and dy. Okay, we like to compare delta y and dy to see what's going on for this situation. So you have y equal to fx. Okay, so y equal to fx equal to x cubed plus x squared minus 2x plus 1. So in this case, you have delta y. So you have delta y equal to fx plus delta x minus fx. Okay, so in this case you have f 2.5, no, not 2.5, it's 2.05 minus f2. Okay, so this guy is 2 plus 0, 0, 5. Okay, so it's 2 plus 0, 0, 5, and your delta x become 0.05. Okay, so this one is going to be your delta x. Okay, so delta y is equal to f 2.05 minus f2. And how could we calculate this one? It's going to be what? It's going to be 2.05 to the cubic power plus 2.05 square, okay, minus 2 times 2.05 plus 1. Okay, so this one will be your f 2.05 minus f2, so it's going to be 2 cubed plus 2 square, okay, minus 2 times 2 plus 1. Okay, so you see that this guy, it can be computed by hand, but it's going to be difficult to compute. Okay, even it is computable by hand. Okay, So you see this guy will be what? This guy will be, if you compute, okay, let's use your phone. So this one is going to be 861 5125, okay, plus 4.2025 minus 4.1 plus 1, okay, and the next one will be 8 plus 4 minus 4 plus 1. So you would get 9.717625 minus 9. So it's going to be 0.717625. Okay, so this will allow you to get delta y. Okay, so this one will allow you to get delta y. I don't need to write delta y, right? Because I already have delta y. Sorry. So what about dy? Let me use other color. So what about dy? Okay, so you have dy equal to f prime x dx. And for this one, you differentiate. It's going to be 3x squared plus 2x minus 2 dx. Okay, and so you have dy equal to, so you have 3 times 2 squared plus 2 times 2 minus 2, and you have dx equal to delta x equal to 0.05 up there. Okay, so this guy, this is what we're going to use. And I use x equal to 2 because we have the beginning x equal to 2. So it's going to be, you just putting x equal to 2 like this. So you have multiply with 0.05. This one is the pink guy. Okay, so in this case, you would have dy equal to 14, 0.05, and this guy will be 0.7. Okay, so you see that the delta y, okay, so this guy equal to delta y, this guy equal to dy, and you see that these two guys are very close to each other. So you see this one is at least 3 digit basically, so it's going to be 2 zeros is correct. Okay, so you see it's 0.71 and 0.7, so this one give you good approximation. If you like to have 2 digit or maybe 1 digit, it's going to be okay for doing this one. Okay, I will give you B on your own. Okay, for B, this one is for A. For B, I ask you to do it on your own. I give you the solution. So delta y is going to be 0.140701, and you have dy, okay, equal to 0.14, and it's easy to compute. Okay, so in this case, this one will be your B. Okay, so for the first one, you use calculator. For the second one, let's do second one. Second one is not that hard to do. So you use 3. Okay, so this one. Okay, so this one I say calculator. For dy, it's going to be just the same thing. 2 square plus 2 times 2 minus 2. However, in this case, delta x turned out to be 2.2 plus, let me write it this way. So this guy is equal to 2 plus 0.01. So you get delta x equal to 0.01. Okay, and this guy will be the number that I have. So this guy will be 14, 0.01. So this guy is about 0.14. Okay, so it's gonna be dy, and you can use your calculator for delta y. For delta y, it's gonna be f at 2.01 subtract f2. Okay, so you use your calculator. Last one, we like to use linear approximation or differential to estimate this one. So the thing that we can do for this one will be we can compute the actual value. Okay, so we can compute the actual value by, so if you like to compute the actual value, you're gonna do the long division. So it's gonna be 3.84 divided by 1. So this one you can use long division. So this one is difficult for sure. Okay, so if you like to compute the actual value. However, you see it's going to be 1 over something like this. So you need fx equal to, okay, so you just use fx equal to 1 over x, okay, just fx equal to 1 over x, and phi, so we're going to let fx equal to 1 over x and phi linearization, okay, and find the linearization at x equal to 4. Okay, so and find the linearization at x equal to 4. So you have f prime x equal to negative 1 over x squared. Okay, so you get f prime 4 equal to 1 over 16 negative. So you have the point. Okay, so this one will give you slope. Now the point will be x equal to 4 and 1/4. Okay, so you use point slope form. So you have y minus 1/4 equal to negative 1/16 x minus 4. Okay, so this one will be Lx equal to y equal to 1/4 minus 1/16 x minus 4. And you want f 3.84. Okay, so you need 3.84. So this guy will be, sorry, I should write this way. So it's going to be, you need 1.384. So this guy is f 3.84 is about L at 3.84. So you get 1/4 minus 1/16, 3.84 minus 4. So you have minus 4. Okay. So in this case, you see that it's going to be 1/4, and everything turned out to be nice because you get 16 over 16. Okay, so it's not 16 over 16, it's 0.16, okay, over 16. So you get 0.25 minus 0.01. Okay, so in this case, sorry, it's going to be positive. Sorry, it's going to be positive. So you get this guy equal to 0.26 for your final answer. Okay, so you have this one equal to 0.26 for your final answer. If you use your iPhone, okay, or if you use your phone, so the actual number for from long division, the actual value is about 0.26041167. Okay, so you see you have about like a 3-digit correct for this estimation. Okay, so for this approximation you have about 3-digit correctly. Okay, so this one is quite good approximation for this value. Okay, so that should be it for chapter 3. In the next video, we're gonna go to chapter 4, which is gonna be about the application of the derivative of the function. Okay, it's gonna be more fun, and it's gonna be the last topic on derivative of the function. After that, we're gonna talk about the integration.